Hello, welcome to another video lecture. This time we want to talk about how do we deal with pulses and wave trains. So you have a system that we are dealing with. There is a oscillator and there's a very long string, and the whole thing has a tension. And the string is not massless, it has mass per unit length that. And if you look at how the wave can travel, means look at the vibration of the particles of the string, we say that there can be a wave with speed v, and v is square root t over mu in this situation. Okay. So at sometime this went up and came down. So it took a little bit. If you look at this, this is y and this is x. Then if you look at y versus t, y at x equal to 0 versus t. So I'm looking at this guy going up. So it went up and came down. So that's the function that tells me the vibration of the string, vibration of the oscillator, vibration of the wave generator, you can call it. And this is not a string, this is a T, okay? Now, it took the string with it, right? And so came back. It creates a wave, which you can say, if this was some x point, the wave would arrive. This vibration will arrive as a wave, which will be moving over there. Because this is a non-dispersive system, it will just maintain its shape. Of course, if you disperse it, this wave will start to spread out as it travels. But right now, we're just looking at this system, a very simple problem. What we would like to know is the energetics of the waves, like how much energy the wave is carrying, right? The power in the wave. We also like to know if I can assign some frequency. Can we build this wave out of harmonic waves, right? So the question is, can we build these waves out of harmonic waves? Answer is yes, and that is the Fourier technique. Answer is yes, and this is called Fourier technique. But what we have here is a Fourier of something that's not periodic, right? This function, if I want to create a Fourier of that function, what the Fourier mean? It can't be Fourier series, not Fourier series. Let me ask you, why do you think it can't be a Fourier series? Let me think about it, right? Think about it. Why wouldn't be? Why? Okay. And turns out I don't have any period. I don't have pulse coming periodically. If you had a pulse ad infinitum, okay? If this was your and this was the y 0t, this I can have a Fourier series. I have a period, so I can have a Fourier series of this, right? But if you have just one of these, I cannot have Fourier series because there is no period. So if I have just one of these, then y 0t. So can't have Fourier series. So this is no Fourier series. So thing is, we still want to we still want to build out of these harmonic waves. It turns out there is a technique. It's thinking of in terms of Fourier integral. What is that? Well, it's kind of, in a way, a generalization of this. When you had a Fourier series, and if this was a period t, then it was made up of period t, t over 2, t over 3, t over 4, sines and cosines, plus constant business, right? So it was made up of functions with periods which were fractions of this, because I had a period. Now, if I don't have a period, it turns out I can still do that, but I have to have a continuous. This will become a continuous values, not just these, but all the way to the 0 period. I have a 0 period epsilon, 2 epsilon, 3 epsilon, with epsilon going to 0 limit. So if I have it, so I'll build out of naught. So the periods I will need, sines and cosines of periods, I will need is 0, epsilon, 2 epsilon, 3 epsilon, all the way, and epsilon go to 0. This is a continuous period. 0 period will correspond to infinite frequency, right? This will correspond to a little bit less than infinite frequency, and then you all of these will epsilon. You can make it epsilon infinitesimal, make it small, so it becomes a continuous, and the series will turn into an integral. So let me write the way we do Fourier transform. I'm going to erase this, and I'll have a separate lecture on Fourier transform. But right now, I just want to show you that Fourier series was a function of t was a 0 over 2 plus an cosine some kind of omega n t, n equal to 1, 2, 3 plus bn sine omega n t, n equals to 1, 2, 3, etc. Right? That was Fourier series. And these omegas were n omega 1, and with omega 1 was 2 pi over whatever the period was. Well, if I make these things and I'm summing over them, right? Basically, I'm doing some catching different frequencies. So this will turn into what do you think? It's going to be some fun. These are basically looking at what the omega is, right? So a function of omega cosine omega t d omega. So that's these two together will go into that, and conventionally I can do 0 to infinity. That will be these two terms. This term will be some other b, just like that, b of omega sine omega t d omega. So this will be f of t, and this does not require a period. Now there's no omega 1 anymore. There's no period needed, right? No period needed. So these are a's and b's that we need in order to do a Fourier transform. So a0 and an, remember there were rules for getting them. So I need to figure out the rules for these guys. How did the rule come up? And it turns out it's the rule for A omega is very similar but not the same, and has to do with the way the integrals work out. Ft, you can have integrals of Ft, summation, it was integral of Ft getting those A's and B's, cosine omega t dt. It's very similar, right? I'm integrating by measuring cosine omega, but there's this pi coming in, and that has to do with I don't have a period anymore. Used to be A's and B's. If you look at an was 2 period over 1 period, and we had a ft cosine omega n t dt. That gives me an, right? But here I have this pi coming in. There's no period. That's a difference. B omega is similarly is 1 over pi minus infinity ft sine omega t dt. So these are corresponding to Bn. The Bn is over here is 2 over t, 1 period, ft sine omega nt dt. Almost similar but not the same. It also turns out that these can also be, in some books, part of that is in the definition of A omega. So you could have said I have pi A omega. You can say let's call it A prime omega, and let's call it B prime omega. With A prime omega and B prime omega, A prime omega will be the pi of A omega. You could just say it like that, and then you can see that this will be just the integral from minus infinity to infinity ft cosine omega t dt. Why do I say that? It's our choice to include the pi inside here or not. If I don't include it, then I have this. If I include it, then you have A prime and B prime omega, which will be just a standard integral. So there is some, in some books, you'll have a different convention. When I do another lecture on this Fourier transform separately, I will actually do it using not sine and cosine and sine transforms, but I will try to do it in a complex notation. Complex notation is more commonly used. This is just for us to see how the relationship with Fourier series emerges. Okay, so I'm going to stop here and do another video right after this on the Fourier transform, and we will work out an example. Hello, in this video I'm going to talk about Fourier transform, and I'm not going to do theory, just write the theorem and then have an example. Okay, so Fourier transform, you can do it in a complex way. So in the complex notation, all you can do, there will be one transform, give you real part and the imaginary part. Or you can do real, and when you do real, you get two transforms, one for the cosine, one for the sine. So you can write down cosine transform, cosine and sine transforms. Okay, so there are two different ways to think about it. Over here it looks very simple, deceptively simple, but simple nonetheless. Algebra and everything is much simpler here, but we'll do both in the example. You'll see. So what it is we have been given, so we've been given a function, periodic, non-periodic, whatever, some generic function. So given f of t, and the t ranges over minus infinity to infinity. Okay, so that's given to us. We will define a Fourier transform of this function. Okay, so by an integral. Okay, so f and we'll call the variable frequency variable omega. Then this will define what f of omega is. Okay, f of omega will be this f of t e to the minus I omega t. For me, it's going to be dt over 2 pi. So this 2 pi is a convention, and we'll just use that convention. We'll say, okay, how do I get ft out? Well, it turns out you can invert this. So, and this will t is from minus infinity to infinity. And you say, what's the omega? Omega is also minus infinity omega infinity. So it's pretty symmetric in a way, right? And ft of omega, you can almost the same except the 2 pi, okay? Minus infinity to infinity from f of omega. And this, if this is plus, then you have reversed the sign. That's going to be plus. And it doesn't matter where you put a plus or minus as long as you have opposite d omega. So this is the convention I'm going to use. This is not always the convention. Sometimes people say, okay, I want to make more symmetric, even more symmetric than this. So you can say square root of 2 pi and divide by square root of 2 pi. That will also work. So some places you have this convention. So when you write a Fourier, when you do this, it may be off by 2 pi, a square root of 2 pi. So unless I know what you have picked as a convention, I can't compare my formula to your formula. Sounds interesting? I can't compare my formula to your formula because you're using a different convention. So Fourier transform comes with a convention, and you got to know which convention your friend used to compare your answer to your friend's answer, right? However, regardless of what I do, the ft that I started with, I'll get the same ft, all right? Because these 2 pi's will all, work out. So it's not completely arbitrary. As long as you give me the pair, then I know how to handle 2 pi. So I'm going to actually do this one. I'm going to do this one because that's the one I did in the book, but I like the symmetric one. But this is the one in the book is that way. Okay, so there was a cosine and sine transform. Well, I'm given the same ft, so this is same given ft, and t is between minus infinity to infinity, and I want to know how to express this into sine and cosine transforms. So I'm going to write the second one first. So I will have something to go with cosine, and then I'll have something to go with sine. This mirrors the Fourier series, right? So I want to go from 0 to infinity. This omega, if I want to have a Fourier series, is going to go from 0 to infinity. And this will go from 0 to infinity. Okay, so let me pause for now. Unpause. Okay, I'm back. So this is a I will say mirrors Fourier series. Fourier series. Because I'm going from 0 to infinity. If you remember Fourier series, right? That also go from 0 to infinity, but only goes integers. This one has no integers. This is continuous now. So I need to find out what these guys will look like. So everything is consistent, right? So I would say A omega is going to be 1 over pi. Now t is going from minus infinity to infinity. It's minus infinity to infinity. F of t cosine omega t dt. And b of omega is going to be 1 over pi minus infinity to infinity f of t sine omega t dt. With all these pi factors will be consistent with that. Because if you go over here in a complex, what is this? This one is complex. Why is that complex? Well, if you look at here, this is complex, and this is real, and this is complex, then this has to be complex. Otherwise, how are you going to get a real from doing this thing? Which means you might say f of omega is f real omega plus I f imaginary omega, and this will be real, but this is complex. You can put these in there, expand this thing, and separate the whole thing out. And you can show, of course, if this is real, then the imaginary part will be 0. It's going to give you some relation. Using that relation, you can show that this will be same as that. And their integrals will be consistent with each other. Okay, so this is the basic definitions. These are there are some restrictions on what kinds of functions you should be able to do and what the ft would be, because this integral has to be doable, right? If you do an ft there and this integral does not exist, then of course it won't work. Same case here. If I have an ft that you give me which is so nasty, has got some problems, and those problems are listed in math physics books. You will see they're called Dirichlet's conditions. But for regularly encountered functions in physics, we won't have to worry about those fine points of mathematical trouble that might come. Okay, so I'm going to do erase this and put a example and work out an example and see what the series, what the Fourier transform, Fourier sine and cosine transform look like, and what a Fourier complex transform looks like for that example. It's a very famous example. And then once we get that, we'll look at the how to interpret the Fourier transform in that example. And other examples of other functions have similar interpretations. The same method of interpretation goes in there. And you will discuss on the other side. So let me pause and erase. Okay, let's look at this example. I have a pulse generator or a vibrator here, and this is a string which is has a tension T in it, and views like that. We still staying with a physical example, although you can think of Fourier transform as a mathematics problem, but we don't want to do that. Okay, so over here, this thing goes up and down, goes up, kind of it stays up for a while and then comes down. So it will give me this kind of function, and so this is my f of t, and this is the t. I want to, you should know that if you do this like that, a little bit later time, this is x, because this is a non-dispersive system, you're going to have a pulse at time t over here. So if you did the x over here, x front, and this is x back, so x front will occur, the wave will get there, because this is going at a speed v, it'll get there, so that if this is the time t, so the t will be equal to xf over v, right? And you can find this the wave going through this, the wave picture of this, through using the retarded time concept. We've done this before in other videos. Okay, so I have this. This is the pulse in time. Not looking shape of the string, it's just looking pulse of this guy going up and down. Very important. Very important to think that this I'm looking at here. Now this is not periodic. Clearly I don't have Fourier series of this. You can say, hey, how about if I just make a copy of this in time and think periodic function. Yeah, I guess you could do that. That would be fine. That's definitely doable. But if this was just the only part I was interested in, that would be okay. But because this is inherently not periodic, that trick is because I want to know for all time. I want to know this for all time. I would not want to copy this for more periods. Okay, just fake periods, not a good idea here. So we have to do Fourier transform, and so we write down. So we're gonna, this is very easy to write down. Function of t is 0 for t less than minus tau over 2. I make it symmetric so it's easy to do the integral. D between minus tau over 2, t tau over 2, and 0 t greater than tau over 2. So this is the function. So I want to write this in a Fourier transform. What does it look like? This looks like some a omega cosine omega t, 0 to infinity t omega. So that will be that, plus 0 to infinity b omega sine omega t. So this is using so-called sine and cosine transforms, a omega and b omega. You can do complex way. Complex will be we use the same letter but use capital letter, and so this is complex. E to the power minus I omega t d omega d omega, but d omega goes from minus infinity to infinity when you do complex. Okay, so we want, if I want sine, because this is a complex Fourier transform. All right, total complete if I know what these guys are. So if I know a omega and b omega, then I've already had everything that I need to know. So how do I do it? So if you may remember that there is a factors of pi, etc., that we have to be careful. So in my notation, in our convention that we're using, a omega will be, has a factor of pi here, and it has the integral ft, which goes from minus infinity to infinity. Okay, and that's just cosine omega t dt. So if I put this thing in there, I'm going to get d over pi. D is a constant, pull them out, minus tau over 2 to tau over 2 cosine omega t dt. Now this is symmetric and this is even. That means I've got two of this, 0 to pi over 2 cosine omega t dt, and that just simply becomes 2d over pi omega sine, this is tau not pi, omega tau over 2. You can see that this is a function of omega. I'm just looking at a function of omega, and sometimes it can be written another way. So if I multiply by tau here, divide by tau here, and then I put these guys together in the denominator, so this is d tau over pi sinc of omega tau over 2. You remember sinc function, sinc x is sine x over x. That's that function. You might remember this function is a it's like a decaying function, like that. It's not 0 here, it's 1 here. Okay. How about b omega? B omega, you see, it's going to end up over here. It's going to be, similarly, will be d over pi minus tau over 2 and tau over 2 sine omega t, right? dt. But this is odd and this is symmetric. That this will give me 0. The odd function will be on the left side and negative integral value. On the right side is going to be right area, right? Positive area, negative area will cancel out, and that should give me 0. It doesn't surprise me because I have a symmetric function in time, so its transform will only be cosine transform. If I have unsymmetric or have an antisymmetric function in time, then our even function in time, and the odd function, this even, and if I had an odd function in time, or antisymmetric, odd function in time, so like if I had this kind of function, then I would have only sine transform, right? Okay. How about complex? When you do complex, f omega will be 1 over 2 pi minus infinity to infinity ft e to the power I omega t dt. Okay, so if I do this out, it's going to be 1 over 2 pi. Ft is d, and it's minus tau over 2 and tau over 2 e to the power I omega t dt. And then it's just d over 2 pi times 1 over I omega times e to the power. So if I have this guy as minus I, the other guy is plus I. If I had this guy as a plus I, the other will be minus I, right? E to the power I omega t over, and that's going to be minus tau over 2 to tau over 2. So d over 2 pi, I have 1 over I omega, and then I've got a e to the power I omega tau over 2 minus is a minus I omega tau over 2. So if I do this, this is going to be, what do you think that's going to be? That's going to be 2 times I sine omega tau over 2. So when I work it out, f omega is actually the same as a omega. Here we have a d over 2 pi 1 over I omega 2i sine omega tau over 2. This 2 cancels that, this I cancels that, so I can do omega tau over 2 and multiply tau over 2. So this is d tau over 2 pi times sinh omega tau over 2. So there's a factor of 2 difference between a omega and this. So the Fourier transform that I got from here is different from that. Then we say, hey, I don't have the same function, right? But I had a ft. How can you give me two different Fourier transform? Well, it's not the Fourier transform itself, but actually the pair that counts, right? It's so I would get this function represented if I try to construct from this function f of t. I'll get the same f of t. If I try to construct from this function, using the complex thing, I'll get the same ft. So let me write that, all right? Okay, so we found that if I did the Fourier transform, I did the cosine transform, I got this. And the sine transform, I got this. But for the complex transform, I got this. They're kind of different values, right? So what this is saying is, how do I get my ft? Won't that give me different ft's? The answer is no, it's going to give you the same ft. Fourier transform is a step in the whole process. So how do I get ft? From here, if I do this thing from 0 to infinity, not from minus infinity. I go from 0 to infinity. Okay, because that's what this was defined as. So if I do a omega cosine omega t d omega plus 0 to infinity again b omega sine omega t d omega, this will give me f of t. So this is 0. So what I get here is an integral from 0 to infinity of this function d tau over pi sinh omega tau over 2 cosine omega t d omega. So this should be is f of t from the theorem, right? So this, if I were to do this integral, I'll get that complicated f of t, which is f of t was written as 0 for t less than minus tau over 2, d for between minus tau over 2, tau over 2, and 0 t greater than tau over 2. So that's the function. It's kind of complicated. You may want to do it. It's a little bit of work, but you have to explore these different ranges for it to work out, right? So if you explore that range in this function, you're going to get 0. If you explore that range, you're going to get the values, okay, d. If you explore that range, it's going to get. So depending on the value of t, what value of t you put there, you are going to get a 0, d, or 0, okay? So it's kind of interesting, challenging, but interesting, very tedious. Interested students should work it out. But it looks like I have this thing here. This is going to be different than that. And the answer is not. Because this is complex, right? So from the complex, how do I get f of t? We did another earlier in the video. This would be not 0 to infinity. When I do in the complex Fourier transform, I go minus infinity to infinity for the omega integral. So this will be, I put f omega, and I think I did a plus here, so it's I omega d omega. Well, if you look at it, let's expand this. I have a minus infinity to infinity d tau over 2 pi. Then I have a sinc, which is a even function, right? Since sine x over x is even function, right? So I might be able to use that property in just a minute. Omega tau over 2 times cosine omega t d omega. Just I can write this as cosine and sine. Plus I will have the same stuff, d tau over 2 pi sinc omega tau over 2 sine omega t d omega. Now notice that this will be 0, right? Sine will be 0, right? This will be 0 because this is even and this is odd, and this doesn't matter, constant. So of course this is even because it's constant, and so together this is odd, but this is range is symmetric. That means this will be equal to 0. That's good. You know, this integral gives me the ft, so I should get the same integral when I work it out here. So I see this is even, this is even. Oh, guess what? The whole thing is even, right? So I can write 2 times just as 0 to, so this will be 2 0 to infinity d tau over 2 pi. Yeah, I got the sinh omega tau over 2 cosine omega t d omega. Well, guess what? This is the same. So even though this is not a omega in this problem, the other one was 0, even though that was the case, the function it's representing is the same function. All right? And because of this happened. In a more complicated situation, you may have more difficulty showing this leads to same, but they should be the same. Otherwise, they're inconsistent, right? So whether you use a sine and cosine transform or the complex transform, it's really up to you. You know, whether you use a sine cosine transform or a complex transform, up to you. But the question is, what do I do next, right? What do I use it for? So if you look at this thing, it's always going to be real. This may be complex. So often we make it an absolute value when we use this thing. And we will see why we have to do absolute thing. But you can't, here it just turns out to be real. That's pretty cool. All right. But in some cases, most cases actually, this will be a complex. And so we have to deal with what interpretation, the real part and the imaginary part, or just the absolute part. We have to deal with that if you use complex. Here both are real. They're going to, by design, they're real. So we can just look at the coefficient of the cosine part, which is cosine transform. I just look at the sine transform. Okay. So we're going to try to plot and try to interpret this result physically. What does it mean? What is when I've got something like this? What's telling me about the pulse itself? Okay. Okay. I rewrote some of the thing. You have we had this pulse, and with the cosine transform I got this. Sine transform was 0 for this. Complex transform was this. We're not gonna really pursue this further here today. But when looking at this, how do I get my function back? This step function. This integral will give me the step function. I'm just making that claim. It comes from the theorem, Fourier integral theorem. That I do this, I get that. I didn't prove it to you. You can look up some math book, and you should be able to prove. You should prove it. Maybe you will do it in math physics class. All right. So right now, when you look at it, so we have somehow this pulse is being constructed from a whole bunch of cosine. This is like a simple harmonic oscillators, right? A whole bunch of simple harmonic oscillators with amplitude that depend on the frequency. So I use infinitely many oscillators. I have one for each omega, and this is the infinite number of them. So if you took this omega, so say I have this is omega, and this is the 0. You can say I have omega, all this omega. So I have one oscillator for each one of these, right? That's that. Then I'm taking amplitude depending on this value. I plug in the value of omega, like omega 0, I'm taking d tau over pi. Some other omega, I'm taking other value, right? So you can see that this itself. What will this? I want to see what the integrand, the net integrand looks like, right? So a omega starts out with d tau over pi, so that's the a omega, and it goes to 0 when this guy is 0, and omega tau was, so if you look at this is sine omega tau over 2 over omega tau over 2. Well, whenever sine is 0, it's going to be 0. So over here is going to be 0. Let me write down over here. So what value of omega it will be 0? That means when this is omega tau over 2 is n pi, and we are only interested in positive values, so the n of this, not at 0. See, this n cannot be 0 because at 0 it's going to be that, etc. So you can see it's best to plot in terms of omega tau, and then I can have a 2 pi here, then I can have a 4 pi here, and so on and so forth. Or if you plot in terms of omega, then you have a 2 pi over tau, 4 pi over tau. So if you plot like that, it's going to come out like that. Well, actually it drops pretty. Okay, let me. So it's about 1/5 here. Say this is 3 pi over tau. So when this is 3 pi over tau, when this will be kind of -1, and so when omega is 3 pi over tau, sine 3 pi over tau over 2, that's going to be -1, and omega tau over 2 is 3 pi over tau times tau over 2. That's going to be 3 pi over 2. This is like, 10, so it's kind of like a 5. So it actually goes below, and so it's -1/5 of this guy, minus d tau over 5 pi, approximately that. So it's going to come down and be maximum over here, and then going to go to 0 again, and then it's going to be the next time it's going to be over here will be it's 8 pi over tau. Then it's going to be 5, right? So it's going to be 5 pi, 15 over 2. That's going to be kind of 7.5 or something. So it's going to be much smaller. And you can see that as far as this guy cosine is concerned, cosine is between at any point cosine depends on omega and t. So it will vary between at different times, right? So this will, so if I take this value, well, it's going to go between -1 and 1, so +1 and -1, depending on what time you're looking at it, right? So, but it's not going to be bigger than 1, so this will have to multiply to that. So it's if you look at it, if I'm over here, that frequency is going to be if I say I'm over here, so if I between 1 and -1 over there also, but then I'm multiplying with that, so it's going to be just between that and that, not going to be make the full cycle. So depending on the frequency, this thing is killing the amplitude of that oscillator. So I see that this says the importance of that up to here I have kind of a whole bunch of contributions. This thing is pretty high, right? So this is the, and when I get very close to the 0, I really start to lose the importance. So which frequencies are important is given by the pattern of this a omega. And similarly, if I were to do this guy, other than this factor, the importance part is contained in how this is behaving, right? So this is just a, those are the specific to this case, but the pattern will be very similar, right? So this will be, so we say this is a main contribution, and then this is first secondary contribution. So it's much smaller in frequency in here, like on average 1/5 less than important as that, and this is 7.5 times as like 1/10. So these get progressively smaller, and so we can define a time, maybe here or here or here, some omega to cut off that. Beyond that, I'm not interested. I want to capture the main effect. So we usually, because it's easy to kind of find this, because this point is very easy to find, so we'll call it a critical omega, okay? Beyond that, I'm not interested, right? So we say, what is omega critical here? So omega critical is the value is 2 pi over tau. So it will correspond to a frequency. So 2 pi frequency critical will be 2 pi over tau. So whenever the time for which the pulse was, so F critical times the time for the pulse was, it somewhat defines a critical one. So if I say, hey, I'm only interested in less than that, I'm only interested in omega less than that, so I'm only interested in less than that. So the frequency that I'm interested in is somehow determined by the time the pulse was on. If the pulse was on, say, for 0.1 second, the frequency of importance is like 10 hertz. If the pulse was on for 10 to the power 9 seconds, it's a very fast pulse, like nanosecond. And frequency, I can be up to the frequency of 10 to the power 9 hertz. So it's actually if you have more more, if the pulse is lasting longer, then you can be, it kind of gives you a range of frequency of importance. Range of frequency is much narrower. If the pulse is lasting for a very short period of time, right, then the frequency is very wide range. Frequency of interest is from zero to that, from zero to that. So we will see that something like this happens in every wave. So when this thing happens in a quantum situation, this is called by another name. Probably you know that probably you know that this is related. The concept is related to a concept of uncertainty principle in quantum mechanics. So we're not going to do this. All classical. This is nothing uncertain here. They're just saying that in the pulse, if I'm thinking in terms of harmonic oscillator, write a pulse in time as a superposition of harmonic oscillators, then I don't need all frequencies to construct the pulse. Actually, up to this frequency would be construct very large percentage of the pulse itself. We'll also see that when we look at the energy in the pulse, that there will be a similar thing, that there will be a range of frequency for which most of the energy is contained in those frequencies. And we may ignore the rest of them. It means it's not there. So all of these are there. Next, what's coming up next is wave train. We want to look at more realistic. A pulse is not that realistic like that, right? So we usually, when we say we use laser, and you turn the laser on for a very short period of time, you might say a nanosecond. But the laser's frequency is 10 to the power 14 hertz. There will be many cycles. It's still finite. Still, so you'll have pulses like that, and maybe if you have a 10 to the 14 hertz and you send 10 to the 9 of a second, you're gonna have about 10,000, right? 100,000. You'll have 100,000 pulses. 100,000 periods inside. But what if you have 10 to the 14 hertz and you maybe you turn it on only for 10 to the power minus 13 second, which is no circuit does that. But suppose you could do it, you'll have only 10 of these pulses. Yes, okay, 10 to the 5 pulses. Even if you have many pulses, you will find that when we work this out, it's going to be very similar, but instead of this, it's going to look like that. And you'll have some central frequency, and then there will be frequency range within which you'll have central, because there is this periodic thing. So this is so this period is t, so this will be 2 pi over t. So there will be some central period, but that's not the only frequency that's present. We're gonna when we analyze this system, we're gonna find that similar to here, find that we have more than one frequency, and we'll be able to characterize how many frequency or which frequencies we need to include most of the effect. Okay, so that's what's coming up next. We'll see you in the next video.